maximum diversity of the seminar series, I'm going to talk about something completely different today, which is decision-focused agricultural research. And as Heiner has already alluded to, I was based in Kenya for a long time at World Agroforestry, and we often had to deal with agricultural landscapes that look roughly like this. So pretty messy, full of all kinds of things, and somehow we were supposed to do kind of impact-oriented research, make some sort of cause some sort of changes here, well, inspire some sort of improvements through our research. And this has actually been very difficult for a long time, and we've been kind of struggling a bit with the scientific approaches that we've been using. And so basically what I'm going to talk about today is inspired by this challenge and the desperate struggle to find some sort of solution for such settings. So I'm a modeler, so we think a lot about modeling. And when we do modeling in agriculture, it's usually driven by some sort of application that we have in mind. It's not usually a pure knowledge generating exercise, but it's often aimed at supporting some sort of decision. Yeah, so we have a model, we want to support a decision. We would like people to make a better decision based on our model, based on our research, and ultimately we want to generate some sort of impact. So this is an impact pathway, as when you work in development, you have to develop all the time to justify the kind of research you're doing. But this requires, if your research is on modeling, of course, this requires models that adequately reflect the reality of agricultural systems. They can't omit very important things, of course, because then your models won't really have much to do with the real world. Now, unfortunately, agriculture is a pretty complex business. It's normally not particularly clean. There's all kinds of stuff going on, as you can see in this image here. And that's not only true in such a drawing, that's true in real life as well, especially, of course, in landscapes such as the one I showed you just a minute ago from Kenya. So the system behavior here depends on a host of different factors and all their interactions. And we sort of have to understand all of them to predict how a system will perform. And decision makers wanting to use models need tools that allow forecasting the behavior of the whole system, not only of a tiny part somewhere. So how can we study the behavior of such a of the whole system and of such a complex system? That's really the question I'm trying to address today. And can our usual research and modeling approaches address this? And well, the question probably implies already that I do see some challenges in the way we usually address modeling that hopefully I can put out some ideas of how we can overcome them. So here's our usual approach to knowledge generation. It's a bit of a caricature, but I think in general, it's not so far off. I mean, we're scientists, right? So we're using the scientific method to do our research. This is what we mostly don't look like, fortunately. So the way this usually works is a bit of a circular process. We make observations, we think of interesting questions, we formulate hypotheses, and then we develop predictions based on these hypotheses, and then we test them. And so we gather data to test the predictions, possibly we refine our hypotheses or alter, expand, reject, whatever, go through this cycle a few times and hopefully at some point develop a general theory, and then that leads to the next set of questions. And then basically we go through this cycle again. It's a fantastic method and it's been super successful in many contexts, of course, but it works best in the kind of the quest for objective and widely valid system behavior rules. It requires that we reduce complexity because otherwise we can't really test hypotheses that we're setting up. And basically we have to first, if we do this in agriculture, we have to first dissect our agricultural systems into small researchable fragments. And in my view, this method really struggles where many disciplines are involved, rules are complex, which is basically always the case when we look at agriculture. So the classic approach, of course, to addressing complex systems is that we try and assemble system models from solid building blocks. Yeah? So we stack up a bunch of studies, different disciplines maybe, until we gain some sort of understanding of how the overall system works. Of course, this doesn't really work well if the blocks don't fit, yeah, which arguably is often the case, even in large projects where we're supposed to work together across disciplines. But the major problem really is that we often can't get enough blocks together. So the cloud you're seeing here indicates the knowledge we would have to have in order to provide meaningful decision support to somebody wanting to manage this system. And the blocks here, of course, don't come anywhere close to reaching that cloud quite yet. But let's look at, I mean, of course, we can do this. We can do one study after another and learn more and more about the system. But let's see what happens as we do this. Of course, with each study we add here, the research effort goes up and the number of disciplines goes up and the funding needs go up, of course. And of course, you can try and get a cluster of excellence going for whatever small decision you're wanting to support, but that's not normally realistic. But of course, as we learn more, the ability to predict system outcomes goes up as well. And that's certainly true, but probably there's some sort of diminishing returns. At some point, well, we've just done all we can really to predict the system performance, and we're probably not reaching full full capacity to predict outcomes in a system that is reasonably complex, at least. So there's usually a large, or there's always a knowledge gap, and I believe in agriculture it's usually quite large. And here we have different things in this gap. There's missing attainable knowledge. So if we just added a few more building blocks, we could find things out for sure. But there are also stochastic and random effects, the biotic stresses that we struggle with, the weather, of course, price fluctuations maybe, and then some fundamental uncertainties in agriculture, like related to the future climate, for example. You can do lots more research and we still won't know exactly what's going to happen. In many developing country settings, at least the risk of conflict is always there. And so there are a bunch of things that even with all the research funding we could eat, we're not going to be able to address. I've added a few more lines here to this diagram, and these indicate knowledge needs for decision making. And so these are possible thresholds that we have to cross in terms of system understanding in order to give meaningful decision support. And it is, of course, possible that the threshold for a particular system we're looking at is somewhere here. And with just maybe one block or two blocks, we'll be able to exceed the threshold. So we do a bit of research and we've learned enough to say something meaningful to a decision maker. It's also possible that we need this 10 million euro 10-year project to reach that threshold. But it's also possible that even with such a large project, we will not be able to generate enough knowledge that we can meaningfully inform a decision. Now, of course, that doesn't usually stop researchers from giving advice to decision makers, especially in developing contexts. There's still quite a bit of that going on. But let's look at what can happen when our model doesn't actually reach the decision relevance threshold. So I have two hypothetical systems here. And what you see on the x-axis here is our completeness of understanding of system behavior. And on the y-axis, we have the predicted relative performance of a monocrop system up here and a complex agroforestry system. So a agricultural system that involves trees and is much more difficult to research and understand. So what can easily happen as we gain more completeness of understanding, we learn more and more about a system, is that we'll always believe, yes, this monocrop system here is superior. So we do a bit of research, we think, oh yes, it's great to just do your staple crops and don't bother with the trees. And after 10 years, we'll still be of that same opinion. So the more we learn, the more, well, the recommendation doesn't change that we'd be giving to a decision maker. So increasing comprehensiveness changes nothing. We'd be right from day one. That would be nice, but I think quite often this is not the case. Yeah? So at some point during our knowledge gaining process, this recommendation actually flips to the other side. And at some point, this recommendation that we should be giving to a decision maker changes, and we would be recommending this agroforestry system. And if we do incomplete research that kind of falls short of getting to this point, we would just be giving the wrong recommendation to someone wanting to use our knowledge. Now, is this completely unrealistic? Does something like this happen? I think it quite often does, and especially in this kind of example here, because many studies on agroforestry systems, they just basically look at the maize yield from the system or the wheat yield or whatever it may be. Yeah, this is usually better in the monocrop system. You can also add more dimensions, maybe the energy produced in the system or impact on GDP or whatever it may be. You could look at direct household income, but at some point you reach a level of complexity where things become a little bit messier possibly. You look at micronutrients produced and you realize, oh, we have fruit trees here and they provide lots of vitamins and minerals. Or you have additional farm products, you take those into account. You have fuel wood, you have timber, medicinal products possibly. Or you look at regulating ecosystem services, things like erosion control, nutrient cycling, positive impacts on the water cycle, etc. And at some point you look at off-farm impacts. How does it impact the rest of the landscape? And the more you learn about it and the more complex your study actually gets, the more likely this recommendation is to shift towards the, well, in favor of the agroforestry system. So what we see here is two problems that are somewhat related. First, if we do an incomplete model, make an incomplete model, we're failing to grasp the full complexity of agricultural operations. I mean, grasping the full complexity is difficult, of course, but we're actually really falling short of getting the essence of what's going on in the system here. More importantly, is that we're inadequately considering our errors and our uncertainty. Because I mean, usually we always consider errors. We express them by a standard deviation, etc. But there's a type of error that comes into a modeling study when we're under complex with our model. Because if we're honestly estimating the resulting errors in such a study here, we'd probably have error bars looking like this. Yeah, and the so we have very large confidence intervals for our prediction at the very left of the screen here, because our study is incomplete. So this error bar doesn't really derive from any sort of measurement errors or anything of the sort, or statistical variation. This just results from our realization that we're not actually looking at the full thing that we should be looking at. We should only draw shorter error bars, according to this reasoning, once we reach a reasonable level of complexity. By doing this, we would avoid valuing at zero all the elements we haven't included, because that is implicitly often done when some people, for example, only do this staple crop yield study, and then they go out to a decision maker and tell them, well, don't bother putting trees. We've shown here that the yields are higher in the pure maize system. Yeah, so implicitly in such a recommendation, everything that was not studied is valued at zero. Now, of course, we don't usually have the budget for doing a huge study that would actually address us allow us to address all the complexity of a system. So how can we possibly do a small study on agriculture? Because it's always complex. There are always many parts involved. Well, let's sketch out an agricultural system according to maybe these components that are shown here. We always have biophysical aspects, we have the economy, we have cultural, environmental, social aspects. And of course, if we have limited resources for research, we have to find a way of studying this somehow. And what's often done is that we only take the biophysical aspects, for example, and then only maybe even a tiny part of this only, because that's all we can really address with the budget we have. So we look at this in great detail and find out lots of things, but the results may no longer be relevant for saying anything meaningful about the whole system, because we've basically blanked out so many other aspects of the system. So the alternative approach could, of course, be that we do a coarser assessment, but that includes all the essential dimensions. Yeah? Here, I drew this in kind of a fuzzy way, so you can't clearly see what's going on, which is a necessary side effect probably of taking this strategy, but you can still see that all the components are represented here. So I think the chances of saying something meaningful about overall system behavior goes up if you do this. But how can it be done? That's really the question we try to address. And for this, it's quite interesting to look at how decision makers generate knowledge. Okay, there's all kinds of decision makers out there, and sometimes we don't want to know how they generate knowledge, but there are good ones who actually have found structured approaches to generating knowledge. And let's look at how these operate. So in structured decision analysis, we don't have a circular process. We have a goal. Yeah, we have a directed process that starts by framing the entire context of a particular decision that somebody wants to take. We will then model this situation, this full decision situation, using all the available knowledge we can easily get, characterize all the risks and uncertainties that are involved, and then make quantitative projections of decision outcomes for the different options that are on the table. Sometimes this already is enough and we can already separate the options and it's clear what's preferable, but quite often we have to then move on and identify key uncertainties that keep us from making a clear recommendation. And once we have these uncertainties objectively determined from such an analysis, we can measure where the so-called information value is high, fill decision critical knowledge gaps, and then cycle through this loop a few times until we're confident that we can recommend a preferable option. Yeah, so this recommendation is the objective of this whole process. And this has been shown to work pretty well in systems that are too complex to fully understand with the available resources, which is very often the case when somebody wants to make a decision. And it's for supporting decisions that must be made without perfect information, which is also almost always the case. So the question we're trying to address here is, what's the best option according to our limited understanding? We didn't make this up. We actually found this method somewhere, and we realized that a lot of great people, great minds of science have been working on this issue of how to make decisions under uncertainty. You recognize some of these names like Thomas Bayes, Judea Pearl, maybe Daniel Kahneman. We've worked with two other people here, Norman Fenton and Douglas Hubbard, who've given us some inputs to our method. But there's really quite a body of knowledge on this issue. How do we address this uncertain situation, and how to make proper forecasts in situations where we just are lacking perfect understanding. So let's see what we can learn from these guys. There are a few key principles of decision analysis that we basically organize our work around. And the first one is that we try and incorporate all important aspects into models. If you want to model a decision and you want your results to be meaningful in a real context, you cannot really omit important things. A little bit, well, we try to visualize here using this barrel, which will be familiar at least to the plant nutrition guys in the audience. This is usually used to illustrate the concept of essential plant nutrients, but I think it also works for model usefulness, which is symbolized here by the water. So in this barrel, you see basically the staves on the side here represent different disciplines that may be involved in an agricultural model. And you see that you can have kind of all the detail you want on nutrient uptake or on photosynthesis. If you don't include and improve your model in terms of the market dynamics or biotic stresses or whatever, you will not really be able to hold a lot of water here, and your model will not be particularly useful in a setting where all of these factors actually play a role. So you then model the system using all sources of information, including local and expert knowledge. You don't immediately start taking expensive and complex and time-consuming measurements, but first try and rake together what is already known. It's important to explicitly consider uncertainties about inputs, about processes, about outputs of a model. So we always use probabilistic models because capturing uncertainty is, of course, important for decision makers, because decision making is a risky business and risks need to be considered adequately. You will then go and identify key uncertainties. So among all these uncertainties that come in, there are usually a few that are really important that we should really be addressing. It's not all of them, and it's usually not the ones we initially had in mind, but there are always a few key questions that we have to address. And for this, there's an interesting concept called the value of information, which is sort of a sensitivity analysis, but not one that's just related to the amount of money we're making, but to the recommendation we're giving. So the question is really, which uncertainties can actually influence the recommendation, the decision recommendation we may be making for someone. You should always be ready to update your model when new information becomes available. That's the last principle here. Back when I was still at Eike, we made up a concept, really. We designed a process to address these challenges. And so the starting point of what we do in this decision-focused research is always a decision that somebody wants to make. So it's a very applied approach in some way. And we turn ourselves into decision-focused researchers and convene a process to conduct a holistic participatory decision analysis that involves the decision makers ideally, because they can usually tell you a lot about what the decision entails. Also stakeholders are involved and academic experts also come in. And together we design an impact model that describes the best of everybody's knowledge in a process-based manner on how the system works and how a decision will impact on the system. We then summarize the current state of knowledge based on all sources of information we can get in literature and wherever we can, we look wherever we can. And we'll also make use of the people who have helped us build the model, and possibly also additional experts. But in order to make them useful sources of information, we calibrate them first, which is a process that helps them get better at estimating the state of knowledge. And I'll talk a bit more about that in a few minutes. So once we have a model and we have the state of knowledge, we can run a probabilistic simulation, make outcome forecasts, and then determine if the decision preference is clear already. Can we already give a clear recommendation? And whenever that's true, then we're basically done. We can make a recommendation, but if not, we have to go a bit further and identify critical knowledge gaps, do decision supporting research, update the state of knowledge, possibly update the model, run more simulations, and then cycle through this process again until we can make a recommendation. That's always the end goal. So eliciting the model structure in this participatory process is something that we've thought a lot about. This is possibly the most nebulous part still of our process, but there is quite a bit of really substantive work on expert knowledge elicitation. So on how to convene a group of experts. Here we see well, some members from our team, Denis Lozanova, who's now at the University of Geneva, the white guy on the left, and the guy in the back here, the other pale-faced person is Corey Whitney, who's still in my group here in Bonn. So they convened this workshop in Burkina Faso here, well, applied a set of group work procedures that we've developed. So this is, it's not so easy to get a group of people to come up with a meaningful model, because there are all kinds of group dynamics that you have to control for. So you don't want somebody, like some pushy person, to dictate the whole process. You want to make sure everybody really contributes their ideas. So we have some ideas and a pretty decent process for this. I don't want to go into too much detail. Well, we apply this, make a model together with these people, and then see what other information we can find. So there'll always be a literature review, possibly in a rather systematic way, to make sure that this really becomes a scientifically robust model. We then go on and develop a conceptual impact model based on what these stakeholders have told us. And here we see one from a study by Marius Rütt, who I think is in the audience, one of my graduate students. In this particular case, we looked at Kaluna production, so an ornamental plant here in North Rhine-Westphalia. And this particular example here simply simulated the effect of applying different fungal management strategies in a Kaluna nursery. So you see the different options here in this this box here, and well, various well, implications this would have for the production process. There's some positive effects, some negative effects, and basically we'd try and sketch out the whole kind of impact chain of these decisions. Ultimately, usually coming up with something like the net present value or the partial farm budget that allow us to compare the different options. Now, once we have a model, we have a bunch of variables in the model, and for many of them, we won't have any data. And that's, of course, a bit of a challenge because we wanted now to estimate our state of uncertainty. Now, estimating the state of uncertainty usually means specifying a probability distribution for these particular values. So coming up with a confidence interval and then a distribution shape, etc. But this is not something that most people are particularly good at. And there's something, well, there's lots of biases that keep us from being good estimators of our knowledge. And I want to just quickly highlight here something, I'm sure some of you will know this already, that gets in the way of estimating things correctly, which is the so-called Dunning-Kruger effect, which illustrates the relationship between our knowledge, our skill, our wisdom, and then our confidence in that knowledge. And unfortunately, I mean, so it would be nice if we don't know anything, we wouldn't be confident, but that's not what happens. Quite often we have people who know almost nothing about a topic being particularly confident in their knowledge. And this is known in this diagram here as Mount Stupid. Yeah, so this is where you find conspiracy theories and things of that nature. And it only, well, it requires learning a bit more about the topic we're trying to talk about until we realize that we actually don't fully understand it and have very little, we feel like we have very little knowledge of the topic. This is the valley of despair. And if we then study a bit harder, hopefully at the end of grad school, we'd be here on the slope of enlightenment where we don't feel quite as hopeless anymore. And we still have and we already also have a pretty good understanding of a system. So this is what often happens. And of course, this is not very helpful. If you wanted somebody to estimate something and he's currently on Mount Stupid, then his estimates would be pretty useless for us. So ideally, we would like to have an appropriate level of confidence that corresponds to the knowledge we actually hold. And same if we go back to these error bars I mentioned earlier, the length of our personal error bars should probably behave something like this. If we know almost nothing, we can still say something, we can say our opinion, but we'd add lots of uncertainty to it. And if we're well informed about something, then hopefully we'll have a bit more, well, have appropriate confidence in our knowledge and would indicate only a little uncertainty, a short error bar. So this is where we want to get. And unfortunately, most people start off as poor estimators of their own knowledge, but there are some processes that help us get better at this. This is so-called calibration training. I mean, we all know that we have to calibrate instruments from time to time, and our mind is also an instrument and it can also be calibrated. So that's been shown quite convincingly that this is possible. And basically, we always start by exposing people to their initial estimation skills. So this usually consists of a set of trivia questions where we assess, well, people have to assess give answers, assess their confidence in the answers, and then in the end, we reveal how often they were actually right or wrong. And usually the results are quite shocking to people, and because they realize how poor they are at estimating stuff. But then we can instruct them in a range of mental techniques that really have been shown to be quite effective at improving our skills at estimation. We then reassess estimation skills, possibly add some more techniques, and at the end of the process, most people really show significant improvement, and many actually reach near perfect calibration. So this has been outlined, this whole approach, the philosophy behind it has been outlined in this book here nicely, How to Measure Anything, by Douglas Hubbard. And there's also a lot of other work on how can we become better at predicting things, how can we forecast results in a credible way. So this is what inspired this. And so once we have now a model and now we have estimates, then we need some sort of technical implementation of our decision analysis process. And for this, we use the decision support package for R, which we maintain in my group. And basically this requires now to take this conceptual decision model we had, construct it as a decision function in R, then feed it with an input table that now provides all these inputs from the data sets, but also from these calibrated estimates from people. So they specify input distributions for all variables. We then run Monte Carlo simulations and then evaluate the results, looking at the outcome distribution, well, basically the comparison of different decision options. We conduct a sensitivity analysis, and then we also do this value of information analysis to identify what additional pieces of information we still need. So what does this look like in practice? I have a few examples for you here from our recent work. The first one is on agroforestry adoption in Vietnam. We had Hoa Do, who was in the arts program, who wrote a paper about a master thesis on an ex-ante evaluation of various agroforestry options. So this is where the study was located, northern Vietnam. And we had so there's a project going on there currently by the World Agroforestry Center, where I used to work before I joined the university here. People are, well, the researchers there together with farmers are trying to implement various types of integrating trees into agricultural systems. These are the options. I don't want to go into too much detail here. This is roughly what that looks like. So this is still early stages and the trees have just been planted, but we already would like to have an idea of how they will perform in the future. So of course you could now wait for 10 years, 20 years and take all kinds of measurements, and then in the end you have data, but that's not really helping if you're kind of eager to roll this, to scale this up, scale this out, so you can actually well, protect these eroding landscapes that you can see here in the back. So people need an earlier estimate of what's going to happen here. And so Hua ran through this decision analysis workflow here, first identified experts here, developed a model together with them, did these probabilistic simulations, post-processing, sensitivity assessment, well, refined the model, and then was able to make fairly good estimates of what's going to happen. Here's a conceptual model. It's not so complicated here. You basically see all the different benefits that the system produces, all the costs, or yeah, some of the cost items here. There's some time discounting, etc. And so basically it allows calculating a net present value for all these different options. And that turned out, so this is what the results usually look like. We have here simulated results for a maize monoculture. This is the return here in, I think, US dollars. So this would be the returns for the maize monoculture. Pretty high chance of fairly low returns. And this would be one of those agroforestry options. So we would be almost, well, we can already see that the potential profits are much greater here in agroforestry than in maize, but we wouldn't be totally sure because, I mean, this distribution here represents our uncertainty. So it's also possible that the real profits would be here in the negative area. So for really getting clarity on this, we can then look at the value of information and realize in this case that we would need more information on the yield of these fruit trees here, Santra, at their peak level of productivity. So this would now be the type of information that the variable we target for additional measurements, additional information. Sometimes measurements is just a measurement so a measurement is always a reduction in uncertainty. That's a definition of a measurement. And sometimes to do this, we just ask a friend who knows. Yeah? So sometimes it's incredibly easy to take these measurements that are recommended here. In any case, agroforestry looked like a pretty good option for almost all these systems. But we also were able to identify these high value variables for follow-up research. So all agroforestry options looked pretty promising, but they require initial investment, which was kind of the main obstacle we found here. A second example is kind of still work in progress. I just call it adapting bananas. We were recently approached by GIZ to help them with an effectiveness evaluation for climate-related measures in banana plantations. The background is that GIZ is working with a coalition on sustainable banana production. So it's German importers, retailers of bananas who want to implement some sort of climate certification scheme for banana plantations. So this, of course, should ideally be evidence-based, and finding the evidence for such a complex thing through kind of bottom-up research would be an endless process, and it's not really feasible. So they approached us to use our approach here. And we were able to put together models, and within a few weeks, we could already give them some indication, and we were able to rank the different adaptation options they had on their list. I don't want to go into too much detail here, but we will basically be able to put together impact models that allowed us to compare these according to a number of different criteria, like climate change adaptation, mitigation effect, ecological impact, etc. So the question here was, can you rank these decision options? And even though we can't precisely predict, of course, how exactly how they would impact banana plantations, but we still have enough information, including well, considering even that everything that's in our model is uncertain, we have enough information here to rank these options and give you meaningful inputs to this certification effort. And GIZ, it looks like they're actually going to use our results now in the design of their certification scheme. Last example is flood-based farming in East Africa. There are quite a few systems in East Africa where people rely on flood water. Yeah? So areas that are regularly flooded, and then you don't really quite know when the flood will come, but normally the water will either be stored in the soil before planting, or the flood may also come after planting, and then people rely on the stored soil water for their production cycle. It's a pretty important agricultural system, feeds a number of million people in the world, including in East Africa. And it's dependent on flood water, but otherwise the systems are very diverse. Here there's just a couple of examples, one from Kenya and one from Ethiopia. Kenya is on top, Ethiopia at the bottom. They're quite different. They have certain characteristics in common, mainly this dependence on flooding, but otherwise they're quite diverse. But of course, as in all, especially smallholder farming settings, the farmers are affected by all kinds of biotic and abiotic stresses. And of course, the soil hydrology is quite particular in such systems as well, which basically means that the classic crop models that we have and are often using in various contexts, they don't quite work in such a setting. So how can we predict crop yields in such a situation? And how can we, and the other question was, can we actually use remote sensing maybe to map the distribution of such systems, considering that they actually all look rather different? So this is difficult, but my graduate student Isufu Liman Haru in Nairobi took on this challenge, and he developed a crop modeling approach. As I mentioned, classic crop models are poorly suited for such a setting, but he produced an expert-informed crop modeling framework for flood-based agriculture using our decision analysis procedures, and was able to set something up that combines Bayesian networks and the Monte Carlo simulation and allows considering many of the things that classic crop models really struggle with. We see the biotic stresses here, for example, are captured. The soil fertility management is here. Different crop types can be considered. We have something on kind of the flood regime and farmer negotiations, which is basically has something to do with infrastructure and institutional arrangements of flood management. So there are a bunch of things, elements of system functioning that he elicited from people he worked with, people who actually operate in such systems. And he was able to put together a model that ultimately allows you to make predictions of the yield in such a system. So we're currently working on the second revision here, and hopefully this will come out pretty soon, the paper on this. He also took on the remote sensing part and tried to map such systems. Also here we have high variation. These systems are highly diverse, and they're also similar to many other land use types. Yeah? So there's certain kind of greening signatures, for example, that you can detect in remote sensing that are also shared by natural systems in floodplains. So also for this, he put together a kind of an expert-informed reasoning engine, a Bayesian network, again, to define characteristic settings for flood-based farming. So basically, he was able to consider soil, suitable topography, soil suitability, some sort of characteristic vegetation pattern. Also, places had to be flooded at some point, and the various other factors. Actually, this is not the whole spectrum here. And he was able to make fairly credible predictions of where flood-based farming in East Africa would be possible. And yeah, he managed to map the high potential areas based on remote sensing imagery, and we finally got the paper out last week, in fact. So those are some examples. Probably didn't tell the whole story, but I hope you got a rough idea. What I want to juxtapose here a bit are two contrasting research paradigms that I see. And one is the scientific method on one side, and one is on the other end of the spectrum, we find this kind of pragmatic approach, this decision science approach. They differ in their main purpose. The scientific method is designed for knowledge generation, whereas decision science is a problem-solving, solution-finding engine. And they excel in different types of systems. Scientific method is great in relatively simple settings where processes are predictable and we can replicate our experiments. Ideally, we only have one discipline involved, so it doesn't get too messy. We're looking for generalizable rules somehow, and well, usually it works well for systems that only follow a small number of rules, because otherwise we get into a situation that we can no longer handle. Decision science is a bit different. It actually does, well, it is designed for complex settings and it can deal with stochastic processes, unpredictable processes, because it's great at capturing uncertainties. It has to operate in situations where we can't replicate, because you can't make a decision 100 times and then see which is the better, in which situation it produces the best outcomes. It can deal with inter and transdisciplinary settings where system behavior is quite context dependent, and yeah, it can accommodate complex and unclear behavior rules. Now, the question as an agricultural scientist, of course, is where are we with our agricultural research? Are we here on the scientific method side, somewhere in the middle, or are we possibly rather far over on the right in the decisions science part of the spectrum? And what is pretty clear is that our comfort zone, based on the training we received, I also received that training, of course, is here. Yeah, we're very familiar with the scientific methods. This is what we really excel at. This is what we can deal with. And we've been sort of trying to stretch this into the other direction quite often. Yeah? You find, for example, in crop models, we try to find out some basic rules and then kind of scale it out to, in some cases, modeling crop production everywhere in the world, and ideally supporting some sort of decisions at that scale even. But maybe it would be easier if we try to reach our objective if we started from the other end. So this is basically the approach that we've been trying to adopt for that reason. So some conclusions. The scientific method, I believe, often struggles in complex agricultural settings. And most agricultural models actually aim to solve problems and support decisions and generate some sort of impact. It's usually not a quest for the basic laws of nature, which means that we need research approaches that can deal with the complexity and the uncertainty of the systems we work on. So pragmatic ways of supporting decision processes. And in my view, decision sciences offer a fitting paradigm, a research paradigm for such situations, because they're geared towards solving problems. They don't aim at precision or at the ultimate answers to complex questions, but at offering comprehensive advice for decisions and for system management. So if solving problems and supporting decisions and facilitating development in complex systems is our goal, well, I think we may consider using decision analysis a bit more and maybe consider it as a useful paradigm for the work we do. Thanks for your attention.